Assalamu alaikum. Welcome to lecture number 27 of digital signal processing. So in this lecture we are going to understand how we can actually design any discrete time filter. Which parameters do we need to design any discrete time filter, and which steps do we need to follow to design any discrete time filter? So that all things will be discussed under this topic, and after that we will discuss the frequency domain representation of discrete time system. Up till now we have discussed the analysis steps of any discrete time system. Now we are more interested in design aspect of discrete time systems, or I can say we are more interested in designing discrete time filters. So just accepting a given set of FIR filter coefficients and analyzing the frequency response, we are more interested to reverse the process and design our own FIR filter. That FIR filter may be of any kind. For example, it may behave as a low pass filter, or it may behave as a high pass filter, or maybe band pass filter or band stop filter. So any kind of filter can be designed. So the first step to start the design procedure starts with the determination of desired frequency response, that which response we are actually going to obtain from this type of system. So after selecting the frequency response, we have to calculate the filter coefficients that will give us that response. Recall in the previous lecture we are obtaining the performance of the filter with the help of its coefficient. Now here we are designing the filter with the desired frequency response, and for that we have to first calculate the filter coefficients that will give us the desired output. So we have to start our procedure by actually deciding first what the frequency response we want for our filter. For example, just for understanding, I have selected a low pass filter design here. You can see the plot. The frequency response is shown in the plot. As you can see, x-axis is marked as frequency and y-axis is marked as h of f, which is the frequency response. And you can notice that this particular frequency response is related to the response of low pass filter, and we can say that this response is of ideal low pass filter, because an ideal low pass filter provides unity gain at the lower frequencies and zero gain at the high frequencies, or in more technical terms we can say low pass filter with unity gain at low frequencies and zero gain or infinite attenuation beyond some cutoff frequency. So cutoff frequency is that particular point after which the gain of the system reduces to zero. So first we have to convert this continuous frequency response in discrete frequency response. So in the next figure you can see we are representing the h of f, which is the frequency response, by a discrete frequency response, and it is very straightforward because the idea of discrete frequency response is similar to continuous frequency response with a little difference, and that difference is the periodicity. You can also notice the difference between the first and second plot. First one is the continuous frequency response and the second one is the discrete frequency response. And you can notice that in discrete frequency response there is a periodic repetition, because discrete frequency domain representation are always periodic with the period equals to the sampling rate, which is fs. But recall the concept we studied earlier. We have to look only at the unique range of the frequency, which is minus fs by 2 to fs by 2, or we can say 0 to fs. Or after learning the concept of FFT, we came to know that the unique frequency range or the spectrum can be counted only for the values of 0 to fs by 2, which you can also see from this discrete frequency response. So basically this discrete representation of the ideal low pass filter is the periodic response as shown in the second figure. Both are the same. First one is continuous frequency response and second one is the discrete frequency response, but due to discretization that response will become periodic. Now the next step after selecting the desired frequency response, the next important step is to determine the filter coefficients, or in this case we have to determine our low pass filter's time domain coefficients, which you can say the impulse response. For this what we can do, we can just take the DFT or FFT of this frequency response to get the time domain impulse response. As we already studied in the previous lecture that the time domain impulse response is related to frequency domain frequency response, as both of these are the transform pairs. So we need to take a DFT or FFT of this discrete frequency plot, and then we will obtain the time domain impulse response, and that impulse response coefficients will be used to design the filter. And the filter coefficients obtained by this way is related to FIR filter coefficients, because we studied in the previous lecture that we can obtain the filter coefficients of FIR filter with the help of impulse response. So the techniques we are utilizing here will give us the FIR filter coefficients. Please remember, if we convert this discrete frequency response into impulse response by taking the suitable Fourier transform, then we will actually obtain the FIR filter coefficients. So to obtain the FIR filter coefficients, we need to define this periodic frequency response over a single period, which is obviously Fs, as this spectrum is repeating itself after Fs. So we need just one unique cycle to obtain the impulse response from this frequency response. And we can here utilize our previous knowledge to actually predict the impulse response of this particular frequency response. Recall the lecture when I take the transform of rectangular pulse and it will resulted in a sinc function. So rectangular pulse and sinc function both are the transform pair. So here you can see I am highlighting in this slide also that this is a rectangular pulse, or if you notice it from m is equal to 0 to fs by 2, then again it is a rectangular pulse. And for this rectangular pulse, we already know that the transform pair of a rectangular pulse is a sinc function. But there we are dealing, or we are converting the rectangular pulse from time domain to the sinc function in frequency domain. But as the two graphs are transform pair, which is rectangular pulse and sinc function, so we can also apply vice versa of it. That is, if the rectangular pulse occurs in frequency domain, so we will get sinc function in the time domain. As you can see, once this impulse response is obtained, we can easily extract the coefficients which can be utilized to design the filter. Actually, the magnitude of each discrete line is representing one filter coefficient. For example, this is 0.219, then this 0.219 is actually one filter coefficient. So all these points are assembled together to formulate the sample set that pertains to the low pass filter. Now it is very interesting to note that as we increase the number of filter coefficients, then our response become sharper. How? We will see it in the later slide with the transform pair of this impulse response in the frequency domain. So here you can see in the first figure we are selecting only few points of the impulse response, or we can say that few coefficients are assembled together to design that discrete time system. Remember, we from these coefficients we actually design a filter equation or difference equation, and as you can see that the number of coefficients are lesser, so in difference equation delay associated with input is lesser, or the delay blocks utilized in FIR filter is lesser. So we can say less filter coefficients, it means less complicated filter design. But on the other hand, if we take back the DFT of this impulse response, which is I want to determine what this time domain representation is producing in the frequency domain. So this response is basically plotting this solid line, which is not a very sharp low pass response. As you can see from the gray line here, this is the ideal response of low pass filter. But as I am not utilizing all the filter coefficients to design the filter, so I am getting this response which is close to the low pass filter but not the ideal one or not the perfect one. From this you can see that the frequencies lies there are also attenuated and the frequencies lie there is also passed through the filter, which is not accepted in the ideal response of low pass filter. However, we cannot achieve the ideal response, but we can get very closer to the ideal response just by increasing the filter coefficients. As you know that sinc function is everlasting, however it tends to 0 or approaches to 0, but as long as we are taking the maximum number of coefficients, then we will get the very sharp response. You can notice it from the second figure. In this figure we have taken the side lobes also, or in other words I am utilizing these samples to extract the filter coefficients, and then these filter coefficients will help me in designing the difference equation, and that difference equation is actually my FIR filter. So which type of response will this filter give? This can be easily calculated by taking the FFT of this impulse response, because impulse response in time domain, and if I take the FFT then it will be the frequency response in frequency domain. So here you can see as I increased the number of filter coefficients, so my response becomes sharper. You can see that slope is nearly equal to the slope of this ideal curve. And in the third figure, if I take the 31 points, then response will get more closer to the ideal one. So this is basically the concept. As FIR filter do not utilizes the feedback, so to get the sharper response or perfect response, I need to add delay blocks. This will complicate my hardware structure as well as the computation time, which I already discussed in the previous lecture, that FIR systems always produces a stable output, but at the sake of its complexity and the number of computation. So here you can see as I am increasing the filter coefficients, as filter coefficient and convolution is very much related, as I can extract the filter coefficients from the impulse response. So this impulse response is actually utilized to extract the filter coefficients, and from these coefficients I designed the difference equation, and with the help of that difference equation I actually designed my FIR filter. And the response of that particular FIR filter can be analyzed by just taking the FFT of these impulse response, which you already see in these three figures. As I increased the number of filter coefficients, then my response becomes sharper. So this is basically the concept behind designing of discrete time FIR filters. Now I hope you can understand this concept, and I would like you people to look for other examples such as high pass filter or band pass filter, how these filters behave and how we can actually design these filters. Suppose we are obtaining this impulse response after taking inverse f50 of the frequency response. So here the impulse response is in time domain, which is informing us the system coefficients for which system is comprised of. So we can write sequence of this impulse response as you can see. The magnitude at n is equal to 0 is 4, at n is equal to 1 is 2, and at n is equal to 2 it is 0, and so on. So we just write the impulse response in sequence or sample set. From this impulse response, which is actually this system coefficient, we can actually design FIR filter, and we already learned how to design an FIR filter with the help of impulse response. We just have to write a difference equation with the help of this impulse response, and this equation is the mathematical representation of the system in which the delayed addition or multiplication blocks are arranged. Recall the block diagram we have learned in the initial lectures. Actually, we were forming a block diagram with the help of this difference equation. So both this difference equation as well as block diagram is guiding us in designing a real-time system by means of mathematical representation or graphical representation. So by developing a difference equation, I can easily develop a system because I know that system is connected in which manner and how the different blocks are connected to each other. This difference equation is formulated in the similar fashion we have studied in the earlier lecture, that is n is equal to 0 here and 4 is the coefficient, then n of minus 1 and 2 is the coefficient, and similarly delay blocks are introduced to add further coefficients. As you can see, there are total 9 delay blocks. However, we can avoid the last two blocks as they are 0 magnitude. So there are total 7 delay blocks in this difference equation. The more delay block we are adding, it means the more sharper response we are getting from that filter. So it depends upon the nature of impulse response, how the complicated is impulse response, and how much coefficients we are obtaining from the impulse response. It will decide the complexity of the system to be designed. From these coefficients, if we omit some coefficient, for example, I can omit the last three coefficients also because 2 are 0 and 1 is 1. So if I just take the first 5 coefficients, then system will give me the response which is similar to the actual response but not the perfect one. But by doing so, I can minimize the cost of system designing as I am utilizing less delay blocks and other blocks which are addition block or multiplication block. So my system is not very much complicated by omitting the last three coefficients, but again I have to compromise on my response which is obtained from that system. So there is a trade-off between the number of coefficients used in designing the filter and the response we desire to obtain from that filter. Well, this is the procedure to be followed to design FIR filter. But imagine if we want to design an IIR filter, how can we determine the IIR filter coefficients that are AK and BK, as you already seen in the standard difference equation form, where AK and BK are representing the system coefficients, and in IIR filters both AK and BK are involved. As you already learned, the design of FIR filter is just by first defining the frequency response which we need from our filter, and then we take inverse Fourier transform of that frequency response, and then shifted that transform result to get the filter's time domain impulse response. But it is very interesting that the desired filter coefficients are exactly the same to that of impulse response sequence, but unfortunately this is not true for IIR filters. However, we can follow the same procedure. Obviously, we can define the desired frequency response of IIR filter and then take the inverse Fourier transform of that response to find out the filter's time domain impulse response. But unfortunately, there is no direct method for computation of its coefficient, that are AK and BK, from the impulse response. So the technique we applied for FIR filter in designing of FIR filter cannot be used to design the IIR filter. So to design an IIR filter, we need some special technique, and the design method actually uses a mathematical transformation known as Z transform. As we already learned Fourier transform, so Z transform is similar like Fourier transform. It is a mathematical tool whose origin is basically the Laplace transform. But Laplace transform is used in analyzing of continuous system, and Z transform is used to determine or analyze the discrete time system. So we need some tool to design IIR filter. So now we shift our focus in those mathematical tools which we require to design an IIR filter, and obviously these tools comes under the frequency domain. So in frequency domain representation, we need to transform our signal, or we need to analyze our signal in frequency domain, and obviously for this purpose we need some mathematical tools, and here are the tools written on the slide which can be used for frequency domain representation. First one is the Fourier transform. You are quite familiar with this tool, as we have a detailed discussion in the previous lecture on this Fourier transform, which is generally Fourier series and Fourier transform. Second one is Laplace transform. Again, very powerful tool, and for system designing Laplace transform is more powerful as compared to Fourier transform, which is the first tool. And third one is Z transform, which is limited to analyze the systems which are represented in discrete time domain. Generally comparing these three tools, which are Fourier transform, Laplace transform, and Z transform. So common characteristic of all the three tools is time domain to frequency domain transformation. These tools take us from time domain to frequency domain. But there are some advantages of each tool over another. For example, Fourier transform. Fourier transform gives us the information of the signal in frequency domain on the basis of frequency. It means that if we are analyzing any signal and if we are analyzing any system, because here we are talking about system, as Fourier is a general mathematical tool, it can be used to analyze signal also and system. And by the system means we are analyzing system on the basis of its response, which is yet another signal. So we are analyzing system with the help of its output or its response, which is yet another signal. So in Fourier transform, we analyzed system with the help of its frequency response. But Laplace transform is more powerful tool as compared to Fourier transform, as it transforms the signal or the information into frequency domain, and it will tell us two things. First one is the frequency response. Obviously Fourier is also telling us the frequency response, Laplace is also telling us the frequency response. Additional information which Laplace tool is providing us is regarding the system stability, which is very important to analyze any system. But this tool, which is Laplace transform, is limited to continuous time systems. We can analyze any system with the help of Laplace transform, which are analog. But as we are more interested to analyze discrete time system, so we need some tool and technique which can analyze digital system or discrete time system. So the third technique, which is Z transform, it is the most powerful tool to determine the analysis of any discrete time system. So if I talk about analysis means just breakdown or to break the phenomena into its fundamental processes to analyze the overall operation. Basically all these tools can be used to analyze. Moving further, analysis can be divided into two major categories. First one is the signal analysis and the second one is system analysis. We have done a detailed discussion in our previous lecture regarding the signal analysis, and we have discussed numerous tools such as CTFS, CTFT, DTFS till FFT. So all these tools were actually designed to analyze any signal, and by the term signal analysis is basically obtaining the spectrum of the signal. So in the signal analysis, our required variable is frequency or omega, which is again radian frequency. But in system analysis, we want to know two things about the system: the frequency response of the system as well as the system stability. So actually these tools are utilized to analyze any signal or system. Generally we prefer to analyze any signal with the help of Fourier transform. We can analyze any signal with the help of Laplace transform also, but Laplace breaks the signal into infinite exponentials, just as Fourier breaks the signal in infinite sine and cosine. So this is the major difference between Fourier and Laplace. Fourier works on sinusoids, whereas Laplace works on exponentials. Laplace actually breaks the signal on exponential. However, we can also perform system analysis with the help of Laplace transform, which is yet very effective, because Laplace tool provide us the frequency information as well as stability information. So basically there are two variables involved in the Laplace transform. First one is the omega, which is simply the frequency, which provide us the frequency response, and the second one is sigma, and sigma actually tell us about the stability of the system. So here we can say system analysis can be divided into two parts. First one is its frequency response and second one is its stability. In Laplace transform, stability is denoted by sigma and frequency response is denoted by omega. And both of these variables combine together, which is sigma and omega, to form another variable which is complex frequency, which is S is equal to sigma plus j omega. It means if Fourier transform is providing us information in two dimension, which is x-axis is obviously the omega or frequency and y-axis is the gain, then Laplace transform is providing us information in three dimension. First one is frequency response, second one is its stability, and third one is its gain. So sigma and omega both combine together to form another variable which is known as complex frequency, and it is denoted by S. However, we can also analyze any system with the help of Fourier tool also, but that analysis is only the 50% of the analysis done by Laplace transform, as Laplace is also providing us the information about the stability of the system. So generally we can say we can analyze any signal completely with the help of Fourier transform, and we can analyze any system completely with the help of Laplace transform. So I hope that these points are clear to you people about these tools. And Z transform is very simple. It is the discrete version of Laplace transform. You can, for understanding, you can say that if we want to analyze any discrete time signal or discrete time system, we have to use Z transform, as Laplace transform is used for analog systems. Or in other words, we can say Fourier transform is a subset of Laplace transform, where sigma is equal to 0, because we are not considering sigma, which is the stability, in Fourier transform. So sigma or stability factor is basically neglected in Fourier transform, and it is just providing us information about the frequency. Now in the later lecture, we will discuss in detail what is the actual mathematical relationship between these three tools, that are Fourier, Laplace and Z transform. We have qualitatively understand that how these tools are interrelated with each other and which tool is preferred in which application, but we have to prove it mathematically also. So we will discuss it in the later lecture how we can relate Laplace with Fourier. What's the relationship between Laplace transform and Z transform, and how we can relate Z transform and Fourier transform.